Can you go back up for 1 second?
Sure. And I just started recording too, so sorry about that. For those of you just watching the video, we're starting with the logistic equation and how it was solved. Population on an island follows logistic growth with an initial population of 500, carrying capacity of 50,000. And I know that after 1 year, P of 1, the population grows to 650. So we want to come up with a logistic model for this.
So that next equation, you just came up with that, like the ky, sorry, the first equation you wrote after the words.
Yes, so this is something you should know or memorize. This is the differential equation that models logistic growth.
Sorry, this question's kind of basic, but so dy over dx, that means the derivative of y in terms of x. Is that what that means, or?
Yes.
All right, thank you.
Everyone good?
I believe so.
Okay, so now we just have to finish these integrals. I'm going to go ahead and pull out this factor of 1 over km. So we've got 1 over km, and then we've just got an integral of 1 over y plus 1 over m minus y dy. And then let's actually throw in this right side of the equation. So all of this should have been equal to the integral of dx. So that'll give us equation relating y and x. Ow, I just hit my funny bone on my chair. Sorry. So what do we get? We get 1 over km. And then we've got natural log of y. And then this term, natural log of m minus y. And then by the chain rule, we'll need a negative. So we've now got 3 constants we need to figure out: c, m, and k. So k is related to the rate of growth, m the carrying capacity. This c will be determined by the initial population, though it's going to get finagled around in our algebra with what sort of generic constant that ends up being. Okay, so sorry, that's a positive 1 over km. Didn't have just stray marks there. We'll combine our natural logs. So we've got natural log of y over m minus y is equal to, let's go ahead and move this km over to the other side. So we'll multiply it over. C can remain c because it's a generic constant. Then when we exponentiate, and then plus a c in the exponent, we commonly bring down and write as a c in front of the exponential. And now we just have to solve for y. So that's all pre-algebra stuff. So that guy times m minus that same guy y, multiply that over. Then we need to bring our y's together. So we added this term over, we factor out our y. And so we get this equation. So how do we solve for our constants? K is going to be the tricky one. And so what are we going to do? Let's see. I'm trying to think of how we might be able to manipulate this. It is common practice, I think, to actually factor out this C. I'm trying to think if that'll make things easier or uglier. I think it'll make things easier. So here's what we can do in the denominator. We can factor out a C. Then these C's will divide. And then this 1 over C, again, C is an arbitrary constant, so we can just label it as a different arbitrary constant. If we want, we can make it like C prime, or you can write it like C2 plus e to the k m x. So how do we solve for our constants? We need to use our initial conditions. So this is the resulting equation. And so the first question was whether or not we can memorize this. Honestly, I do not agree with memorizing something like this because it won't be useful. You will never use a memorization for this. And if you do remember it, it's just a pre-calc level of understanding. We do actually teach this in pre-calc by simply giving this equation. Now, other things we can do, let's to simplify ourselves. We've got M. I'm going to label this as just, I'm going to relabel K as K2. And so one of the problems with this type of equation is we did have 3 constants that we need to solve for. But because they get shuffled around in the work that we solve for, the ultimate resulting equation we can model in this form, and it'll be much easier to use these constants and solve for the constant now as written. And so for simplicity's sake, we're going to relabel the constants. I'm just going to actually drop the subscripts. So just note that this K is different from the K in the original differential equation. Slightly different. Of course, they are related up there. So how do we find our constants now using our initial information? We know that P of 0, and I guess to be more precise, we should call it Y of 0. So since I started using Y to represent our function for our population, Y sub 0 we know is 500. So we plug in 0 for X, and we're going to get M over C plus 1 is equal to 500. We actually may want to just solve for M first. The carrying capacity is the limit as X goes to infinity of Y of X. In other words, it's going to be the limit as X goes to infinity. Kx over C plus e to the kx. So what's our limit to infinity? We have exponential over exponential with the same order of growth in terms of the exponential. Both have the same base, which means that these are going to essentially cancel each other out, and we will get m over 1, or just m. And we know that since this is our carrying capacity, we should approach 500,000. So that's our m. Wait, is that what I chose? There's just 500 or 50? 50,000, excuse me. So since m is 50,000, then C is going to be 99. And then lastly is our rate of growth, this K, which might be a little tricky to solve for. So we now have our model of y is equal to 50,000 e to the kx over 99 plus e to the kx. And so we know y sub 0. We know that y sub 1 should be 650. And so we're going to have 650 is equal to this. So we just plug in 1 for x. And now we're going to solve for k, which probably isn't going to be done because we'll have 650 times 99 plus e to the k equals 50k e to the k. And solving for e to the k might be a pain. So 650 times 99, we will have 650 e to the k. Subtract that over is equal to, so whatever 50,000 minus 650 is. And so our e to the k is that. And so that computation, it's a little lengthy. Of course, we would take the natural log of that to solve for e to the k, or to solve for k, I should say. Nothing that complicated is going to be on the exam, though, at least in terms of the numbers you have to compute. Other questions? We've got cross sections and work problems listed in the chat. See if we can find a good cross section problem. Hmm. Well, I do not see any cross-sectional areas on any of the past exams. Does anyone have an example they want to go over, or a specific type? The thing about cross-sections is it depends not only on the area that we're integrating over, but it's going to also depend on what type of shape. So the shape is often what makes things difficult. So it could be semicircles. We could have right triangles in various orientations. We could have equilateral triangles, squares. Anyone in specific that you guys want to go over? Let's take a look at the book. See if we can find a good problem. So we can do something like so we can have the region bounded by 4 minus x squared and the x-axis. And we could say something like cross sections are perpendicular to the y-axis are, what's your guys' favorite shape? You can do semicircles, squares, equilateral triangles. We could do right triangles, isosceles right triangles.
Can you do equilateral triangles?
Equilateral triangles. Okay, so in terms of our picture, what does this mean? This means that we are slicing horizontally. Slices are perpendicular to the y-axis, and then they're coming out above as equilateral triangles. So our triangles are going to look like that, where the middle of the triangle right there, so that line going into the page now is the y-axis. And this distance is x. So half of the base is x. We need to figure out the height. In an equilateral triangle, all of the degree measures are 60. So if the short side is x, hypotenuse is 2x, this one's going to be square root of 3x. So here, let's call it h. And so h is square root of 3x by our geometry. So our volume what is our dV? It's going to be our cross-sectional area, and we're going to need that as a function of y times dy. So in our problem solving methods, we drew our picture, got started with our equations, labeled our variables, and of course now that we're getting into these equations, we see well, we need everything in terms of y, and so that's going to be a little bit more work. So we need to solve this guy. That so x squared is 4 minus y. So x is plus or minus square root of 4 minus y. Positive x on the right, negative x on the left. And so what is our area as a function of y? Let's pull out that piece. I know area is 1/2 base times height. The base of our equilateral triangles is going to be 2x. The height is square root of 3x. But again, we still need our dependence on y. So now we want to convert our x's. So this is going to ultimately just be square root of 3 times x squared, which is just going to be square root of 3 times 4 minus 1. So now we've got our area as a function of y. So our volume, square root of 3 times 4 minus y dy. And then the bounds, y's go from 0 to 4. Other questions? Someone mentioned work problems. You got to give me more specifics than that. So which type of work problem you want to cover? Those ones are definitely on the previous exams. And we also have a suggestion for sequences. So particular questions. What about sequences?
I'm taking the limit.
Limits of sequences, yeah. Let's see. Looks like on this one they covered series. It's probably during the semester. So here we have an old exam. It's written a little weird. I don't know why they have these. This was from spring of this year. We've got a couple sequences. Determine whether or not the sequences converge or diverge. So an is cube root of 3, or sorry, cube root of n over natural log of 300n is our first one. And then our second one, we've got cosine of n factorial over square root of n. So with one, what you want to do we can simplify it a little bit. I'm going to write this as natural log of 300 plus natural log of n. We can pick a function exactly like n. And see what happens to this function. So we calculate the limit at infinity. And of course, we're going to get infinity over infinity, indeterminate form. So because of the natural log of 300, or the reason I did that is because I anticipated using a L'Hopital's rule here. You can kind of anticipate a L'Hopital's rule. If you just plug in infinity in both the numerator and denominator, take n getting larger and larger, we're going to get infinity over infinity. So from the get-go, I kind of saw that L'Hopital's rule's going to try to play a role for this guy. This one, if I plug in infinity for here, cosine of infinity doesn't exist. So there's not really a L'Hopital's rule for this guy. You can essentially treat sequences exactly like functions. And so anytime you're seeing an infinity over infinity or a 0 over 0, you can anticipate L'Hopital's rule. And then you want to do exactly that with a function with the same closed form as n, essentially. And so by L'Hopital's rule, we've got the limit as x goes to infinity of the derivative of the numerator, derivative of the denominator. So that's why I pulled out the 300 there. Make the derivative a little easier. Don't got to do a chain rule. Then what do we want to do? We want to simplify. So we've got 1 over 3 x to the 2/3 times 1 over x in our denominator. And so we've got the limit as x goes to infinity of 1 over 3 over x to the 1/3. When we do all the simplification, And so now minding all of those fractions, and fractional exponents, we see that the power of x, it'll be an x to the 1/3 in the numerator. And then so as x goes to infinity, we'll get infinity. And then with our other one, we've got to be a little bit more clever. Over, what was the denominator? Square root of n. Now, unfortunately, when we plug this in, we get a does not exist over infinity. Right? Cosine oscillates up and down. And as I compute cosine of various values of n, or even n factorial, it's going to be oscillating up and down. So that limit doesn't exist. And so whenever we get something like this, does not exist over infinity, it is in some sense an indeterminate form. But we can't really use L'Hopital's rule because does not exist is different from infinity. Infinity is oftentimes denoted as undefined. It is a limit of the set of real numbers that doesn't exist within the real numbers. Whereas does not exist literally means that it doesn't exist. There isn't a single number that would be able to model it. So we have to be a little more clever, and this will come up with cosines and sines quite a bit, is the squeeze theorem. And comparison tests. So we did comparison tests for integrals. Essentially the same thing holds for sequences, that we can bound cosine between 1 and -1. And I wanted to give my space to write in there, because as soon as this function is bounded between these two functions, we can compute the limit of everything. And what do we get? Well, this limit, since the 1 is constant, the denominator is going to go to infinity, so that'll be 0. This is the one we're trying to figure out. And then again, this limit, since the denominator is going to get infinitely big, will approach 0. So here I have a number, or at least a sequence, where at infinity, it's going to be between 0 and 0. So this guy has to equal 0 by a squeeze theorem.
I have a question.
Yeah.
Under what circumstances do you have to change the n to an x and like solve it like that?
That's hard to say. You kind of have to eyeball it and get used to doing a lot of these, because if you think it converges, that's a good tool. So if you think the sequence will converge, if you can show that the function converges, then the sequence will converge.
So like, should you just use it every time? Like why did you not need to use it here?
Well, here it wouldn't have helped us because cosine of x factorial, one, we don't have an x factorial. And
Wait, can you say that one more time?
we don't have a cosine of x. We can't have a continuous variable x and have cosine of x factorial. This doesn't make sense.
Okay, gotcha. So like for just like do it most of the time, like change it all to X.
If there's no factorials, usually you can to get a
Okay,
set.
got it.
Yeah.
Oh, and then so does it converge if the limit like exists but it doesn't equal 0, does it still converge?
Yeah. As long as it's a finite number.
Okay, got it. So yeah, okay, cool. Thank you.
Other questions? Someone asked about applications to physics and engineering. You guys got to be a little more specific. So pick out a problem because there's a million different examples in that section. Work problems that are appearing on Spring. Looks like we've got a center of mass problem. We've got bag of sand being lifted. We've got no work problems here. No, here, centroid. So center of mass. And then on this one, looks like we've got, once again, a center of mass problem. Here. Which ones do you guys want to do? Center of mass. Let's check this guy out. Consider region R composed of a semicircular region and two rectangles. The centroid of the semicircular region is located at -1 minus pi over 4 over pi. Assume that R has uniform density rho. Find the following without using integration. So this is a good example to do. We haven't done one. Didn't get to one of these specific ones in class. We did do center of mass. So let's draw this guy. The height of the box is 3. And width is 3. And we've got a little smaller rectangular region, length 3.
All I'm seeing is your screen share.
Yeah.
Oh, okay.
I still got to switch that back. I was drawing it real quick. Just to give you guys the picture. And then it looks like we've got a circle. Center is at -1. And then the radius is 3. So something like this. kind of helps to draw it ourselves because we want to put it in the centers of mass. So we want to be able to do this without using integration. So the centroid of the semicircular region is located at -1, -4 over pi. So this point here, -1, -4 over pi. So what we want to do, we want to break this down into known shapes. It's kind of like what we're doing with integration, except instead of integrating, we're just adding up individual parts and using symmetry and geometry to find individual centers of mass. Right, for our formula for the y, the moment about the x-axis, when we weight everything by y, it's y distance. We kind of came up with some fancy formulas of breaking things down and slicing things into bars and then finding the middle of the bar. We are in some sense just doing the same thing. We're actually doing an easier version of that. So the center of mass of the triangle, or excuse me, the square here, this 3 by 3 square, should be right here. And what are those coordinates? Well, it goes from -1 to 2. So the x center is going to be at -1/2, or excuse me, +1/2. And then 1.5. The center of mass of this guy will be right here. And what are the coordinates of that? We've got to go, so -1, -2, -2.5. And then 1/2 on the y-axis. So our total mass in this case is just going to be the area times the density. Let's label some things. Let's call the blue one 1. That'll be our square. Let's color the semicircle green. And the rectangle looks like it's going to be red. What did I say? 1, 3 here. Sorry, let's call this guy 2. So our area, maybe we want to label it as area total, area tot. And we want to add up the areas of each region. A1 is equal to 9, 3 by 3. A2 is equal to 3, and A3 is radius 3, so 9 pi. So it looks like we were going to have 12 plus 9 pi for our total area, which means our mass is going to be 12 plus 9 pi times rho. Now, when we compute the moments, the moment about the y-axis is the sum of all pieces of individual mass, all pieces of mass weighted by their x coordinate. So we haven't quite gotten to this. This is a sigma. We'll learn that Tuesday once we start series. Just consider this as the sum of, let's say the weighted sum of masses by their x value, by their x coordinate. So what we want to do with these guys is consider this whole square. You want to consider the entire mass just centered at that center of mass. The entire mass of this rectangle condensed down to the center of mass. Likewise for the circle. So if I only have 3 points and 3 masses, we can find the moments just by doing a discrete calculation. So trying to think of how to label this. Moment about the y-axis from mass 1 is going to be the total mass. So mass 1 of course we can find by the area times density. So it's going to be 9 rho times its x coordinate of 1/2. The moment or contribution to the moment of inertia from mass 2 is going to be the size of the mass weighted by its x coordinate, which is minus 5/2. And then the moment of y3 its mass weighted by its x coordinate. And then what you want to do is just add. So going to look like a mess. What are we going to get? 9/2 minus 15/2 minus 9 pi.
Oh, quick question. Would the 9 pi be divided by 2 because we have half of a circle and not a whole circle?
Did I find that area wrong? Yeah, 9 pi over 2. Thank you. So our area would be adjusted as well. What's that give us? Negative 6 over 2 minus 3 minus 9 pi rho.
Should be 9 pi over 2 for that one too, right?
Did I miss that one? Yep. Did. So that's our y moment, our x moment. We want to do similarly. We weight all the coordinates, all the masses by their y coordinate now. So it's going to look very similar. Running out of space here. Next 3. So we're going to have 9 rho, 3 rho, 9 pi root 2 rho. and then weighted by each of their y coordinates. So mass 1, 3/2. Mass 2, 1/2. And mass 3 was minus 4/pi. So we're going to get, here, let's just add them all up. 27/2 plus 3/2 minus, pi's are going to cancel, 2 is going to cancel. I'm seeing minus 18. And then everything times rho. So what is that? So 27/30/2 is 15 minus 18. Looks like we were getting minus 3. So that is our moment about the x-axis. So then if we wanted to solve for the centers of mass, or the center of mass, the x-coordinate, we would take the moment about the y-axis divided by the total mass. The y-coordinate, we would take the moment about the x-axis divided by the total mass. Sorry, I missed some of your comments. Looks like some people were saying sandbag. You guys want to do that one too?
I'd find that helpful.
Yeah, let's take a look. This is why, like, I mean, let me know, because, I mean, when you say work problems, give me a specific one, because there's a lot of different ones, and each one's going to be different. Center of mass is going to be completely different than this sandbag problem. So take a look. We've got 11-pound bag of sand lifted at a constant rate. Hole in the bag cause sand to leak out 0.3 pounds per second. Suppose it takes 10 seconds to lift the bag 7 feet off the ground. Okay, so let's write some of this down. Says let f of x represent the weight of the sand at x feet above the ground, between 0 and 7. Find f of x. So here's my picture. This is my bag of sand, some sort of rope around it, and it's leaking sand. It gets lifted a height x. Max height we're lifting is 7 feet. Other things we know is that f of 0 is 11 pounds. We also know that the sand is leaking out of the bag at 0.3 pounds per second. So our trouble with this problem is we have 2 independent variables at the moment, both x and time, where x is our height. Remember that work is force times distance. So we need force as a function of x. That's our first task in this part. And then it says, suppose it takes 10 seconds to lift the bag 7 feet off the ground. I think, yeah, other key phrases. Lifted at a constant rate. So what is lifted at a constant rate? It means rate of change of x is constant. We're lifting it constant rate. So how do we want to think about this? Well, we've got the force, the weight of the object, is going to depend on the height, and the height is going to depend on time. So we can use chain rule and sort of related rates problems to come up with what f of x should be. Let's come up with our functions here. So let's come up with x as a function of time. Well, if we know that dx dt is c, of course, x needs to be call it x naught, a linear function where m is our slope. And we know it takes 10 seconds to lift 7 feet. We can assume x naught is 0. Since it doesn't tell us a reference point, but it says we are lifting 7 feet. So wherever we begin that 7 feet of lift, we can mark as 0 height, which means that our initial height is 0. So at time 0, our height is 0, which means we can solve for the rate of increase. So our x of t is just 7 over 10's t. Likewise, we are given df dt. And we are given a constant rate, or df dt is constant. So, which means f of t is going to be minus 0.3 pounds of sand every second that we're losing, plus the initial amount of sand. So you could solve that, of course, simply by integrating this, and you get minus 0.3 t plus a constant, and then knowing that at time 0, we are at 11 pounds. We would solve for that. 11 is our constant. So we've got this equation and this equation. I have f as a function of t, x as a function of t. How do we find x, or excuse me, f as a function of x? Simply find the inverse. Let's find time as a function of x. In other words, given a height, I can know what time corresponded to that height. And then since this is t, we can plug that in for our force now, for the weight of the sandbag. It's going to be minus 0.3 times 10 over 7 x plus 11. So that's going to be minus 3 over 10, so minus 3/7 x. plus 11. In other words, every foot we increase, we're losing 3/7 of a pound. And now the work integral is pretty easy from that. Our work as we had was just the integral of f dx, which is then minus 3/7 x plus 11 dx. And we are lifting from 0 to 7.
Should that be 0? Should that be 0 to 10 for distance?
10 was the time. So look at the problem carefully.
Oh yeah, my bad. Sorry.
Yeah. So 10 seconds to go 7 feet high. Yep. Other questions?
Could we do a surface area question?
Yeah. Let's see if we can find one. I thought I saw one earlier on one of these exams. There we go. So we've got exam 2 of last summer, 2020, and problem 2 here. Consider the curve y is equal to √3/2 square root of 16 minus 4x squared on an interval -2 to 2. Find the area of the surface obtained by rotating the curve about the x-axis. So we've got this guy about the x-axis. How do we graph this guy? It looks like it's going to be an ellipse. So I don't know how well you guys are able to recognize ellipses yet. Ellipses are like circles. Like if it looks circular, like 1 minus x squared or a constant minus x squared, it should be a circle. But as soon as you start finagling these constants to be different sizes, it usually ends up being an ellipse. So you can always pick values of x. So for example, if we pick 0 for x, square root of 16 will give us 4. Cancel that 4, and it'll be square root of 3. Great y value. And then how do we make this guy vanish? So when x is 2, plus and minus 2 at our endpoints, 2 squared is 4, times 4 is 16. 16 minus 16 gives us 0. So those are our, let's see, so that was square root of 3. Square root of 3 is somewhere between 1 and 2. So it looks like this. It's got an ellipse here. And then we are rotating it about the x-axis. So we've got this egg-looking shape. But we're only considering the area, the surface area. So we've got these guys kind of wrapping around these strips. So what do we want to do? We want to add up the area of each strip. And so remember, each of these strips had some arc length. So for a big picture, right, if I'm pulling off this strip, the center of rotation here, this distance is y. And so what is the circumference here, right? If this is ds, then the circumference here, let's call that c. So c is 2 pi r, which means the area of that strip is 2 pi y times ds. Now this guy, we've found an arc length formula. Same thing. Namely, it's going to be square root of 1 plus dy dx squared dx. So all in all, what is our surface area going to be? Actually here, I think the book uses capital S. It's going to be the integral of 2 pi y. I'm going to convert to f of x square root of 1 plus f prime of x squared dx. So this is one way to do it. If we were to set up this integral, we've now got some messy constants here, but maybe it won't be too bad. 16 minus 4x squared times, now 1 plus f prime of x squared under a square root. So 1 plus. This is our f of x. Times negative 8x. So kind of a messy derivative. Sorry for the scratch work. Let's try to squeeze some things in. We've got a square root 3 over 4. The other thing that's going to be in the denominator is this square root of 16 minus 4x squared now. And then we've got a minus 8x in the numerator as well. Oi, so that's messy. I like to do these. Let's do these and let's reorganize it. Let's just give ourselves more space. So we had our formula. Let's have S is 2 pi f of x square root of 1 plus f prime of x squared. So a lot of times with these, I like to just find this as sort of a side scratch work. We had f of x is square root of 3 over 4 square root of 16 minus 4x squared. So f prime of x was square root of 3 over 4 times square root of 16 minus 4x squared times negative 8x. Simplifying a little bit. Actually, so we can cancel that 4 and 8 out. And then the other thing I like to do, even as scratch work, is square that. And now when we plug everything in, it'll be a little bit simpler to start with. We won't have to do so much of the algebraic simplifications within the integral. So we still got some messy constants, square root of 3 over 4, and then we had 16, square root of 16 minus 4x squared for our f of x, and then square root of 1 plus this guy. Dx. So hopefully everyone can kind of see where we got the pieces from. Big parts of these problems are just knowing your basics, knowing the essentials, computing your derivatives correctly, doing the algebra. Because we do want to compute this surface area. Some of the surface area problems say like set it up, but don't compute it. We just want to check to make sure you can set it up. Same thing with some of the volume problems. This one says find the surface area. So we do want to be able to compute this. Let's pull out all the constants. So it looks like we are going to have square root 3 pi over 2. We've got our integral. Now, I want to bring this whole guy, 16 minus 4x squared, underneath that square root. So everything is under this one square root. And now when I distribute this guy, it'll cancel this term down here for that second term. So that will make our lives a little easier in terms of these fractions and writing everything out. And so it looks like we've got an integral of the square root of 16 minus x squared dx from -2 to 2. I haven't been writing the bounds. So it gave us the x bounds -2 to 2. So those weren't hard to figure out. And now, question for you guys, what's our next step to solve this integral?
Can we do a trig sum?
Trig sub, yep. So what is our trig sub? We want x squared to be 16 sine squared so we compute our x and our dx. This is going to be 16 times 1 minus sine squared, or 16 cosine squared, all under a square root. So 16 cosine squared under a square root gives me 4 cosine. And now, oops, bounds aren't -2 to 2 anymore. Let's simplify the constant. Square root of 3. Looks like we've got 8 square root of 3 pi times the integral of cosine squared theta. Do we want to find the bounds real quick? So x was 4 sine theta. I like to find the bounds if we can. So whenever x is 2, we're solving the equation 1/2 is sine theta. So theta is going to be pi over 6. And so theta will be minus pi over 6 to pi over 6. So when x is -2, it'll just be -1/2 equals sine theta. Remember your inverse trig and the appropriate domains and ranges for your inverse trig. So your theta's minus pi over 6 to pi over 6. Or of course, you could always back substitute at the end. And then how do you do the integral of cosine squared? You remember the half angle formula. Which looks like it's going to be given to you. So check your formula sheet. Cosine squared x is 1 plus cosine 2x all over 2. They give you the moment formulas too. There was a question in the chat, do we need to remember the surface area formula? It looks like you might have to. I would study the surface area formulas and know where they came from, both surface area and arc length. Let's double check. Let's see what other formulas they give. Usually they just copied the same formula sheets from the previous semester and used them. So if they haven't appeared on any of these guys, I would say make sure to memorize those formulas or know them, know how to get them for arc length and surface area, looks like. Okay, so then finish off the rest of the integral. Minus pi over 6 to pi over 6. We've got 8 root 3 pi times 1/2 theta plus sine of 2 theta, and then over 4. And we're evaluating from minus pi over 6 to pi over 6. So 8 square root of 3 pi times, we're going to have pi over 12 plus 1/4 sine of pi over 3. And sine of pi over 3 is root 3 over 2. We plug in the negative value, we'll get a negative pi over 12 plus 1/4 sine of negative pi over 3 gives us negative root 3 over 2. So all in all, collecting all of this mess, it looks like, so that negative is going to distribute. Those two terms will be the same. We'll times 2, 16 square root of 3 pi times pi over 12 plus root 3 over 8. So this, essentially. And with this pi, we're going to get some pi squareds and some messy things. So 16 over 12 is 4/3. We'll have a pi squared plus root 3 times root 3 will now cancel. So 9 times 2 gives us 18.
Should that just be 3 pi instead of 18 there?
Which
Or,
one?
I'm sorry, the 16 root 3 pi times root 3 over 8. Shouldn't that just be what 2 pi times 3? So 6 pi.
Yeah, I did 3 squared, not square root of 3 squared. So it should just be not 3 times 2. So it should just be 6 times pi. Other questions?
Hey, could you go over finding closed form expressions?
Ah, yes. Let's see. I don't know. I don't know if we've seen any like that. Hmm. So we've done a couple of limits. There's some more limits there. Let's see if we can find any in the book. The best example is going to be doing it from a recursive sequence. Let's see if we can find one. Yeah, let's see. Let's just go over the basics then. I can't find one in the book, and there's not one on the previous exams. So the basics for finding those, if you're given recursive sequence, let's do 3 of them. So let's say 1, we just got an, let's say n plus 1 is equal to an plus 3 with a naught equal 7. Let's say we've also got n plus 1 is equal to 1/2 an, and they give us a naught is let's do let's see 384. I think will work. Be a decent starting number. Yeah. And then let's do something a little more exotic. So an plus 1 is equal to an plus, I think we want to do 2n plus 1. We'll see if we can come up with something like that. And we'll say a1 is equal to 1. Let me see, check that real quick, see if that will give what we want. Yeah, I think that would be good. Cool. So whenever you want to find a closed form expression, especially from a recursive sequence, always write out terms first. So if we start with number 1, our first term we're given is 7. So a0 is 7. How do I find a1? It's going to be a0 plus 3. How do I find, excuse me, and we can write these out. A1 is a0 plus 3. A2 is a 1 plus 3. And a3, a2 plus 3. And so we can see what's happening with our sequence. Of course, we are just adding 3 every single time. So our an, it's a linear sequence. Anytime I'm adding a constant to get the next term, and that constant is the same, it's a linear sequence. Starting value is 7. Slope was 3 for every increment. For number 2, what do we have going on? Our A0 was 384. A1, the formula says, is going to be a half of A0. So that's going to be 192. A2 is going to be half of A1 by the recursion formula. So it's going to be 96. And A3, half of A2. We're down to 48. And then the last one, or at least the last one I want to write, A4 is half of A3, so 24. So our sequence looks like this. And what is happening to get each consecutive term? We are dividing by a constant value, or I guess more precisely, we like multiplication a little bit better. So multiplying by a half every single time. Excuse me. And if we are multiplying by a constant every time, that is our R in a geometric series, or I guess you could call it the base of the geometric series. Excuse me, geometric sequence. And of course, the other word we have for that is exponential. So we know that our AN should be an exponential sequence. I like to use B for base. R is kind of like the rate of growth, commonly used in exponential functions, especially for interest and things like that. Mind the starting value. The starting value was 0, meaning if I plug in 0 for n, it will solve for that A0. If it starts at 1, sometimes you have to you can shift and write this b to the n minus 1. Any questions on that one? So it's all about writing the sequence and essentially recognizing the type of form it is. The key ones you should recognize are exponential and linear. If the terms are increasing at a constant rate, linear. If they are being multiplied by a constant value to get the consecutive terms, exponential growth. Other than that, it should be like blatantly obvious. So like this next one that I wrote, we have an plus 1 is an plus 2n plus 1 with a1 equal 1. So of course, A1 is 1, our starting value, of course, mind that. Our A2 is then going to be A1 plus, so our N is 1. So 2 times 1 plus 1, which is going to be 1 plus 3, so it gives us 4. Our A3 is going to be A2 plus 2 times 2 plus 1. So that'll give us 9. And A4, 9 plus 2 times 3 plus 1 gives us 16. So our sequence looks like that. And that is the sequence of squares.
So between that and finding limits, is that pretty much all we're gonna need for as far as the test goes?
I think so. Let me check real quick. Yeah, that's basically it. I mean, finding limits is going to be a big thing. And then I guess the other thing is knowing some basic recursions and then finding the closed form expression for it. Other questions? Got about 8 minutes. I'm getting pretty tired. I can answer one more if you guys got one. Other questions? Otherwise, good place to call it. Hopefully this was helpful. Cover some last minute things. Make sure you guys remember those formulas. Arc length and surface area. Practice those word problems. May want to get up tomorrow, practice a word problem or two before the exam. Get a good night's sleep. It is imperative for learning. And other than that, I will see you guys tomorrow morning.